And thank you to Golden Valley Electric Association. As you might have just noticed the pop-up, we are recording this meeting or this class because we know that some people were unable to join us at exactly this time. So you can just acknowledge that this meeting is being recorded. So now let's go on to the next slide, please. As I said, I am Dana Trufermoda. I work at the Cold Climate Housing Research Center as a building scientist. The class instructors today are my colleagues, Connor Dennehy and Vanessa Stevens. Connor is an energy auditor and Ness is a building scientist. Here are their short bios. Connor Dennehy is an energy auditor and researcher at NREL's Cold Climate Housing Research Center in Fairbanks, where he collaborates on high-performance residential construction projects through energy analysis, mechanical design, and workforce development. His research efforts focus on cold climate-appropriate building technologies, especially HVAC technologies. Vanessa Stevens is a building scientist and project manager at NREL's Cold Climate Housing Research Center. She has been teaching educational courses on a variety of building energy topics for over 10 years, and many of her projects involve retrofitting houses to be safer and more energy efficient. Joining the three of us behind the scenes is Lauren Chris Carboy of Information Insights. She will be running the polls. She is also letting all of you folks on. She will be helping with transferring any questions that you might have from the chat box into our spreadsheet so that we can give them to the instructors, and helping with everything Zoom related. Talking of Zoom, next slide, please. We will be going over Zoom etiquette on the next slide, and also some expectations for those taking this class for CEUs. First though, let's do a poll. We will be asking you to do several polls throughout the class, and so this is a chance to practice. Lauren, please launch the poll. So question number one is, where are you from? Are you from Fairbanks, Anchorage, Matsu, Kenai, and elsewhere? And then if you scroll down, how did you hear about this class? Was it through GVA newsletter or social media? Was it through the Alaska Center of Energy and Power weekly newsletter? There are multiple other choices. And lastly, if you scroll all the way down in that window, why are you here today? Do you need residential endorsement CEUs? Are you interested about learning about heat pumps? So I will let you do that poll, and we'll be back in about a minute. So it looks right now that we have quite a few Fairbanks from the Golden Valley Electric Association's area. We also have Gino and a couple folks from South Central, Anchorage and Matsu so far. And how you got information about this seems to be CCHRC and Golden Valley, as well as Alaska Housing Finance Corporation, the Alaska Center for Energy and Power, and other. And then scrolling down all the way to the bottom, a lot of people are interested in learning about heat pumps. That is great. So Lauren, I think we can close that poll. And now for Zoom etiquette. Please mute yourself or we will mute you, and also turn off your video camera if the instructors are speaking. It is less distracting, and also it takes less bandwidth for everyone else. For the polls, please do answer these. They help us improve the classes for the future. feel free to raise your hand. That is, if you hover over, well, preferably if you have any questions, put them into the chat. There is a chat box that's on the bottom. If you hover your mouse over the screen, you should see a chat box on the bottom. You can click it and it will pop up. You can put your question in. You can also close it and then click on the chat button again, and it will pop it back up. Now, if you are getting CEU credit for this class, the CEU credit for this class is specifically for builders. If you are a realtor, please join us on the for a Thursday class in 2 days. That one offers CEU credit for realtors. So if you are getting the CEU credit for builders, please be engaged. Please answer the polls that we put in and ask questions if you have them. Stay the entire time, and then at the end, within the next 2 weeks, I'll mail you the CEU certificate. In order for us to do that, please make sure that your Zoom name that we can see here matches the one that you registered with and that you want on the certificate, because I will be matching the registration list with the audience list here. If you want to rename yourself, you can, on the right side, you can click on the participants button on the bottom of the screen. You will see the participants, including yourself. You can then click on the 3 dots next to your name and you should be able to rename yourself. Let me just check that I have covered everything. And I believe we can go on to the next slide. So for the outline of this course, Connor and Ness will cover what are ductless heat pumps, how they work, types, advantages, disadvantages, and the cold climate best practices. Then they will go into the best practices for energy efficiency retrofits in Alaska, because energy efficiency goes hand in hand with heat pumps, because you want to use as little energy overall as possible. And they will cover energy audits, and finally, resources. So, Connor, please take it away.
I think it's actually me next, Dana.
Oh,
thank
yes,
you.
Sorry.
No worries. Well, thank you, Dana, for getting us started and setting a good example on pace. I tend to be a fast talker, so I'm hoping I can match Dana's nice slow speaking. We do have a poll on this first slide just to get a sense of how many people have heard of heat pumps, since that is what we're going to start out by defining. Lauren, I'll give you a second. I can't see the polls since I'm sharing slides, so I'll give you a second to do that.
Okay, it should be up. And for those that can't see the poll, the questions are, have you heard of heat pumps? Does your house have a heat pump in it? And have you built or worked on a house with a heat pump? If you're not able to see the poll, you might have an older version of Zoom, and in that case, you can answer in the chat. It looks like about 96% of people that are answering have heard of heat pumps. The majority don't have a heat pump currently, and most have not built or worked on a house with a heat pump.
All right, well, thank you guys for answering all those questions. I'll go a little faster through the super introductory material then, and we'll get to the later slides about advantages and disadvantages and like cold climate considerations. So just starting off, what is a heat pump? So heat pumps are pretty cool devices because unlike a furnace or a boiler or an air conditioner, they can provide both heating and cooling to a building. And they use renewable energy to do so. So heat pumps gather heat from a renewable source. So in the case of ductless heat pumps, they're gathering heat from the air. There's also ground source heat pumps, or ones that are located with the loops in seawater. So in all those cases, right, the sun is providing heat to the air, ground, or sea, and the heat pump's gathering it and then using it to heat a building. Because a heat pump also uses electricity, so it does require electricity to run a refrigeration cycle. Whether or not the heat pump is entirely renewable depends on the source of electricity. So in many places, and we tend to use Southeast Alaska is an example because they have more hydropower than the rest of the state. You would consider a heat pump an entirely renewable appliance because they're pairing that renewable heat from the air or the ground with the renewable hydropower electricity. Here in Fairbanks, where I'm located, and Dana and Connor, we usually call them like partially renewable appliances, since you're definitely tapping in to the renewable energy, the heat in the ground or air. But at the same time, we're using electricity from the grid, which has some renewable sources here in interior Alaska, but we also do rely on coal and oil natural gas for part of it. So we would say a heat pump is a partially renewable appliance. How they work. Most people already have a heat pump in their house. So that's kind of a cool fact. Heat pumps are the exact same technology that you find in your refrigerator. So I have a little bit of a diagram. This would be an air source heat pump in heating mode. If you take a second and think about your refrigerator, it's gathering heat from the inside of your refrigerator using the coils on the inside. It's running it through a refrigeration cycle, and then it rejects that heat either through the coils in the back of the refrigerator, or sometimes you'll find them on the bottom. So same concept, right? But now we're looking at a house. In this case, the coils on the outside of the house are gathering heat from the surrounding air, running it through that refrigeration cycle. So that's the part that uses electricity. That compressor in particular is using electricity to kind of step the heat up to a temperature that's more usable for space heating. Then it's going into the indoor side of the appliance and, quote unquote, it's rejecting that heat into your house, or it's releasing the heat into your house. And then the cycle just repeats all over again. Most heat pumps can do both space heating and cooling. So you flip a switch and it literally just reverses the cycle. And in that case, it's working the same way that your refrigerator would work, except instead of cooling off the inside of your fridge, it's cooling off the inside of your house. So it's gathering heat from the indoor coils, running through the refrigeration cycle, rejecting that heat outside, and then running the cycle over again, if you're looking to cool your house. As I kind of been mentioning, there's two different types of heat pumps, ground source and air source heat pumps. We're focusing on air source heat pumps today, but I just want to get everybody on the same page that there are other types of heat pumps out there. There's quite a few ground source heat pump installations in Alaska. We have a couple hundred here in the interior. And then I have a picture here of one that's installed at the Juneau Airport. This type of heat pump also encompasses heat pumps that might be gathering heat from a water source. So for instance, in Seward, at the Sea Life Center, if you've visited there, they have a heat pump that's actually gathering heat through some coils that are in the ocean. And then even here in Fairbanks, we have some houses that are near just kind of gravel ponds, gravel pits, and they have their ground loops sunk to the bottom of those. So they're gathering heat from the water. But on an air source heat pump, you're gathering heat just directly from the outdoor air. So I have a picture there of just a compressor. The coils are right inside that box and you can kind of see through them. There's a fan that helps move the air over those. One thing about heat pumps, especially air source heat pumps and much less so ground source heat pumps, is they do have a little bit of a challenge in cold weather. Okay. I'm a math person. If you're not a math person, you don't have to look at the graph, but I do have it on there for anybody that likes graphs. Heat pump efficiency depends on the amount of heat that they can gather from their source of heat, be it air or ground. And if it's the ground, the temperature tends to stay pretty stable over the year. Certainly the ground gets colder in the winter and then it warms up in the summer, but that range of temperatures is a lot narrower compared to the outdoor air temperature. So when we're talking about an air source heat pump, on a 40-degree day, we would still want to be heating our house. And at 40 degrees, that air source heat pump has quite a bit of heat that it can be gathering from the outdoor air, running through that compressor, getting it to a higher temperature, and then using it to heat your house. But as the temperature falls, there's less heat available in the outdoor air for that heat pump to gather. So the heat pump has to work a little harder and it becomes less efficient. It's having to use more electricity and less of that renewable heat that's available in the outdoor air. Unfortunately for us, colder temperatures when the air source heat pump is becoming less efficient is the exact time that our house heating demand is going up. So we do have a little bit of a problem here. That being said, manufacturers are well aware of this issue. Literally every year there's new heat pumps coming out on the market with a variety of different strategies to address this and keep heat pumps operating at a higher efficiency, even as the temperature does get colder, so that it's still an economical heating device. If you're listening from Southeast Alaska, for the most part, you can heat year round with a heat pump. One issue that we do have in interior Alaska is that there does become a temperature where the technology just cannot keep up with the lower outdoor temperatures, and the heat pumps, will have a cutoff. Depending on the model that you have, it can be anywhere from, 10 above to, I think the latest cold climate models go down to -20. So there are models out there that can heat for the majority of the year here in Fairbanks, but when we hit those -40-degree days, it's going to be a day that your heat pump doesn't work, even at a low efficiency. So that's kind of just another challenge that we see with heat pumps in colder climates. In the same way that heat pumps can gather heat from different places, either the ground or the air, they can distribute heat in different ways. So they're a very flexible appliance. All of these different types are on the market. So you can kind of fit the air source heat pump that you buy to your needs. Air source heat pumps can be in an air to water configuration, to where you can distribute the heat through your house using a hydronic system. So that photo is just of an air to water heat pump that was in our lab. The compressor on the outside looked just like some of the pictures that I've shown, a box of outdoor coils that gathered heat from the surrounding air. But instead of taking that and heating air inside the house, it actually heated water that was inside that tank there. So it's water that you can use to heat like a radiant floor. In some cases, you can get it hot enough to heat with a baseboard hydronic distribution, or there are like air to water heat pumps that can be used to make domestic hot water even. So air to water heat pumps certainly exist. That middle picture, we do have air to air heat pumps that then you would distribute the air through your house using a duct. So this would be similar to like an oil-fired furnace that heats the air, and then you have a system of ducts that takes the air to your living space, to your bedrooms, to all the rooms in your house. I just have the main duct in this picture, but you can imagine it could branch off into different places. And then the final type of heat pump distribution that we see with air source heat pumps is actually an interior head. And this one's a little bit different because instead of transporting heated air through your house, it actually takes the heated refrigerant line. So there's a refrigerant line that just goes directly into this interior head. And then it heats air right there that blows into the room. So, a lot of times when we talk to people, we say that this is kind of like a room heater, almost analogous to like a Toyo stove. So you'll just have this one interior head, and it's providing heat to the space around it. There certainly are systems where, there's maybe one or two outdoor compressors and then they go to different heads inside, but it's all the transportation is happening with the refrigerant. And so the distribution is just a single point source of heated air. So there's no ducts involved in a ductless system. There's a couple different types of ductless heat pumps. So I'll just point these out really quick too. Very similar to a Toyo stove, you can actually have a ductless heat pump that goes to a floor mounted distribution system. So if you don't like the wall mounted version, you can have the box on the floor that's just sending heat out. The wall mounted systems were the most popular. They were kind of the first configuration of ductless heat pumps. That's that middle picture there. And then these days they also sell ceiling mounted versions. So if that's something that would be interested for you in your house, there is ways to distribute this heat a little bit differently. And just one more point on these ductless systems, they are room heaters. So again, like we always compare them to a Toyo stove. And you can see, like, for instance, in this house, they have an outdoor unit. That's the yellow box next to the porch there. That's the thing that's gathering the heat from the outdoor air, cooling down that outdoor air as a result. And then you'd have a refrigerant line to the interior head, which is that yellow box right there in the dining and living space. So just like a Toyo stove, it's heating the area. And then you're kind of relying on like an open floor plan to get that heat to the rest of your house. So, you know, it's going to heat that open area fairly well, but then as you are getting back into those bedrooms, it's definitely going to be a little bit more of a challenge to get heat from this one point source, you know, blowing hot air all the way back there. Different people do different things with ductless heat pumps as a result of this, because it's not really a whole house heating system. If you have a larger house, you can certainly just use it to displace heat and then rely on some kind of backup heating system to get heat into those bedrooms, maybe your entryway in your bathrooms, whether that's an oil-fired boiler or furnace. Or what other people will do is they'll install like little electric room heaters in those bedrooms just to boost that heat up to a little bit more of a comfortable temperature, especially if you have like a closed door and that heat isn't moving around the house as much as you would like. So that's a specific thing to those ductless models that are becoming really popular. So I wanted to point it out because they've certainly taken off like in the warmer climates of Alaska. So like in Southeast, and you even see them in Fairbanks, especially for people that want to use them for cooling in the summer and then maybe heating in the shoulder seasons. I am going to get into a little math here. I warned you I like math, but when you're looking around at heat pumps, you might notice this term coefficient of performance. So I wanted to explain a little bit about what that's about. If you stop thinking about heat pumps for a second and you think about oil-fired appliances, a lot of times when you go shopping for them, you will, or you're looking at them online, you'll see an AFUE, which is kind of a percentage that tells you how efficient the appliance is. So when you look at this AFUE number, you'll see a percentage like 85%. And what that's representing is how much energy that's in the fuel that you're using gets into your house. So if we're talking about a Toyo stove and you go and buy a gallon of fuel and that Toyo stove has an AFUE of 85%, it means 85% of the energy that's stored as chemical energy in that fuel eventually makes it into your house. Unfortunately, the rest gets lost up the stack or up the chimney of your oil-fired combustion appliance. Similar with biomass, you're always going to have a little bit of heat lost up the chimney. So with heat pumps, we don't have any combustion. So we can't really use the same like percentage efficiency measure. So instead they use what's called the coefficient of performance. And ultimately it's the energy that gets to your house divided by the energy that you have to buy from the power company. Give you a little bit more examples here. You can think of coefficient of performance of an efficiency. In some cases, a COP of 1 would correlate to an efficiency of 100%. So that would be a toaster. Think of your electric oven, your toaster, an electric baseboard, an electric hot water heater. They all have a COP of 1. That means for every unit of electricity that you buy from your power company, you get 1 unit of heat into your house, into your domestic hot water tank. The COP of an electric heating appliance, it never changes. Okay, if we start looking at heat pumps, let's pretend the COP is 3. If the COP is 3, that means we buy 1 unit of electricity from the power company and we get 3 units of heat into our house. That's pretty awesome. And again, that's just because of that renewable heat that we were able to access by gathering it from the surrounding outdoor air. That's what's allowing us to get more heat into our house than the electricity that we're buying. Okay, the one challenge with COP with heat pumps is that it's not a steady number. So it very much depends on that outdoor temperature that I was talking about. The more heat that's in the outdoor air, if we're talking about like a 40-degree day, we can reach those higher COPs of 4 and 5, because there's heat available for those outdoor coils to gather. The compressor's not having to work that hard in order to step up that heat for your house. On the other hand, if it's a day it's -10, there's not a lot of heat outside, then we're looking at a COP, you know, maybe in between 1 and 2. We're still a little bit more efficient than the toaster, but we've lost a lot of the efficiency because there's less heat to gather and that compressor is having to work harder. So the COP changes. That's a little difficult for manufacturers to report. So when you're like online trying to figure out, okay, what heat pump works for me, you know, you have to kind of take those numbers with a grain of salt, because there's never going to be a number that can accurately represent how your heat pump is going to act all winter long. And honestly, we wouldn't want it that way, because that would be super expensive for the manufacturers to have to go and test their heat pump at every single different outdoor temperature that existed. So what they will do is they'll kind of give you the seasonal COP number, and sometimes they represent it as HSPF, or heating season performance factor. It's analogous to COP. There's just different units on it. So with either one, HSPF or COP, you're looking for a higher number, right? Higher number means higher efficiency. And manufacturers will report this out at different temperatures. I'll have a graph of this later. But for instance, they'll say, okay, let's just pretend that your winter is 40 degrees every single day. You know, here's the COP that I'm going to report. And then you kind of have to do a little bit of work on your end of saying like, well, how often am I at 40 degrees? How often am I above 40 degrees? How often below? And do a little bit of interpretation about what that manufacturer's COP means for your specific situation. I will show some more examples of COP on the next slide, but I did want to talk a little bit about defrost cycles. This is a challenge that any kind of air source heat pump, ductless or ducted, faces in cold climates. And what happens is because the coils are outside, they can end up forming ice on top of them, and that makes them less efficient. You know, that ice is kind of blocking those coils from being able to access the heat and the outdoor air that they need to gather. So lucky for us, manufacturers have come up with this defrost cycle way to melt the ice off those coils. And what happens during a defrost cycle is the heat pump actually runs in reverse. So it's basically running in cooling mode. It takes a little bit of heat from your house, it puts it out to those outdoor coils, and it uses it to melt the ice off. The problem with defrost cycles, even though they're a necessary thing, is that they lower the efficiency of the heat pump. Again, for math people, there's a graph here. The blue dots on this graph are the power that the heat pump is using. So you can kind of see like, okay, we're chugging along there at the beginning. It's getting in power. The green dots are the heat that's going to the house. So exactly as we would expect, right? We're using electricity, we're putting heat into the house, but then you can see right there, kind of after 1:30, this heat pump goes into a defrost cycle. So you can see it's still taking power, but there's no heat going into the house. And the reason for that is because in defrost, it's actually taking heat from the house and it's putting it on the outdoor coil to melt that ice off. You can see a little power spike, it goes back into its normal heating mode, same as it was before. We're using power, we're buying power from the power company, we're getting heat into our house, no problem. And then, yeah, you can see towards the end of the graph there at 3:30, another defrost cycle happens about an hour later. There are some things that you can do in order to prevent defrost cycles from happening as often or to make them a little bit shorter. This is a picture of the outdoor unit of a heat pump that's actually in North Pole, so just south of Fairbanks. And the installer did a few things to kind of help with these defrost cycles. For one, they custom made a little bit of a hood to go over where the coils are, and that's just to keep snow and rain off of those coils. You know, certainly you're still going to have ice form the same way if you had like cold soda on a hot day, you still get condensation on the outside. So, you know, it's not entirely dependent on snow and rain, but certainly keeping the snow and rain off the outdoor coils helps. And then the other thing that they've done to make things a little easier here is you can see this heat pump is lifted off the ground. It's sitting on this base that they've made out of those wooden blocks. And the reason for this is because when defrost cycles occur and that ice melts off the heat pump, you know, it has to go somewhere. So that water is dripping down onto the ground and we want to give it a place to where it can go. It refreezes into ice. And this was actually one of the first heat pumps that was installed in the Fairbanks North Pole area. They didn't used to have it on the stand. And the very first year that they ran it, it formed so much ice underneath the heat pump that it actually ended up jacking the heat pump off to the side and it broke the electrical connection and it stopped working. And so that was like one thing that they learned in the process was, okay, we need to lift this thing off the ground, give there a place for that ice to form without causing a problem for anyone. The last thing I'll say about defrost cycles is they are somewhat manufacturer dependent. So the manufacturer is the one that's setting the control scheme for the defrost cycle. So, you know, there's still going to be defrost cycles sometimes when there's not actually ice on the coils, but at the same time, we can make them short, hopefully by doing a little bit of help on our end. I have one more graph. Hopefully you guys are math people too if you're in this class. Just one last thing about COP. So the first thing I want everyone to notice about this graph is just the general trend, right? It's kind of a bunch of dots that represent COP of 3 different heat pumps. And, you know, if you look at the graph kind of from left to right, they go up. So the x-axis here, you know, going from left to right, that's the outdoor temperature. And then vertically, we have the COP. These are actual COPs that CCHRC measured of 3 different heat pumps a couple years ago. And you can see exactly what I was talking about, right? On those warmer days when there's a lot more heat that's available, we see higher efficiencies of heat pumps. And then unfortunately, as the temperature is getting colder, that efficiency is dropping off. If you look at that one particular heat pump that is represented by the red and the green dots, at like 45 degrees, that thing was reaching COPs of 6. Like, how awesome is that? Like, by 1 unit of electricity from the power company, you get 6 units of heat into your house. You cannot beat that in terms of this type of technology. Okay, on the other hand, if we look at the other corner of the graph there down at the bottom, when we're looking at temperatures of 0, -10, there was only one of our locations that hit those temperatures during this winter, and that heat pump, the efficiencies are represented there by the blue and the purple dots. We had efficiencies down of 1, like, you're just as well off heating your house with a toaster. And then you can see, because of some defrost cycles that were occurring, we actually had heat pumps of below 1, or excuse me, COPs of below 1, in which case you're better off heating your house with a toaster or like an electric resistance appliance. And so you can really see that temperature dependency. The other thing I want to point out about this graph is what I was talking about, if you're going online and looking at different heat pump models, trying to figure out which one might be the best one for you. Manufacturer COP is sometimes representative of what is going to happen here in Alaska, sometimes not. So, there's a blue square on there, and that was the manufacturer seasonal COP. You can read given at 44 degrees Fahrenheit. For that particular heat pump that's represented by the blue and the black dots. And certainly, it acted exactly that way, at 44 degrees. It was exactly as the manufacturer said, but winter isn't always 44 degrees. So you did see that range of COPs. It got higher as the temperature got higher, it got lower as the temperature got lower. Now the red square, it ended up being represented by those green and the red dots. It actually performed better than the manufacturer's spec was predicting. And some of that just comes down to operating conditions, whether or not it's operating at full load, partial load, if it's running all the time, not running all the time, that there's some dependencies there. But in that case, whatever heat pump they bought, this heat pump was a Wrangell, it ended up performing a lot better. And then that last one that's represented by the turquoise star down at the bottom, the dots representing the actual COPs actually came out lower than the manufacturer specs. So that's just what I was saying. The manufacturer specifications, they do have some value, but you have to take them with a little bit of a grain of salt for your particular situation. We're going to switch things up with another speaker. That way you guys aren't just listening to me drone on for a long time. So Connor is going to talk a little bit about advantages and disadvantages of heat pumps in Alaska, and then just some cold climate considerations. So Connor, if you're there, I'll let you take it away and just let me know when you want me to switch the slide.
Yeah, thanks, Ness. Hi, everybody. I'm going to round out mostly what Ness was talking about throughout the presentation. As you can tell, are heat pumps appropriate for you? It depends on a lot. So we're going to summarize some of that here. I'm going to give you a few resources. And then in the back half of this presentation, we'll go over a lot of the front end energy efficiency things that will dictate whether a heat pump is actually appropriate for your location or not. So the first things to think about is how can this benefit you? You could have potentially reduced energy costs. It depends on where you live, what your power structure is like, and what your local climate is like. As Vanessa mentioned, it's technically a partially renewable resource utilizing outside air or ground temperatures. And so as long as outside conditions are favorable for you, you've got a pretty much infinite amount of heat source available to you. There is no combustion on site here, so that's great for your local outdoor air quality where you live. And depending on the mixture of the energy sources for your grid, this can be beneficial for your entire local area. Kind of pairing with that, obviously no need to purchase fuel oil or natural gas in that same token, but we're kind of thinking, I guess, with a little bit of a Fairbanks lens here. So there's a lot of disadvantages to having fuel oil on site. You have to get it delivered. It's generally always a little bit of spillage. Sometimes you can run out if you don't know exactly how much you've got out there. It could be a colder winter than you were anticipating. And during times like these where prices are rising, there's tends to be occurrences of people actually stealing fuel. So having a heat pump on site eliminates that because you're solely using electricity for it. And in thinking about ductless heat pumps, they're essentially a very low maintenance appliance for you. So there's a few things, some air filters and other things to take care of, but for the most part, there's not a whole lot to it for a homeowner. It mostly falls on the service technician. Another advantage of the heat pump is the ability to cool. So it provides you that ability during the summer, which is pretty great. I'm gonna mute that question. Sorry. You also have the ability to program the appliance to operate on a schedule. Depending on your existing system, you may already have that ability, but you've got more flexibility with these systems. They come with a remote control, so you can, depending on the room that it's used in, you can tailor it for the fit of that room. And then there's a few options for filtration, which I mentioned before. And so that'll kind of take us into the disadvantages of ductless heat pumps. Is starting off on that note, there are limited options for filtration. So if you're comparing this to a traditional forced air system where you can really take advantage of a large ducting system to put in a large filter, a thicker filter, so you can really clean your indoor air, you don't have that ability with a ductless mini split. Likewise, continuing on with some of the disadvantages, depending on where you're living in the state, probably going to need some backup heating. And that's either for your design winter temperatures or beyond what the heat pump can deliver, or you need to make sure you'd like some redundancy in your system. So in the event of a power outage or something like that, you want to be able to use your wood stove. So it's good to have an integrated system. You have to think about how those systems integrate with each other. So you have to plan through that. You don't want to just have a slapdash approach to that. And been thinking about the design winter temperatures, you've got your cutoff temperature. So you've got to keep in mind how all of these systems interact with each other. And then the ductless mini splits, they have the compressor outside. It's generally a really quiet system. There's a lot of stigma around compressors outside. That's a technology that's progressing every year. Likewise, when Ness mentioned that they're operating at colder and colder temperatures every year, they're also getting quieter and more efficient every year. But there's a possibility if your neighbors are very close by, they may notice when your compressor cuts on, and you could have a conversation with them. Likewise, if you're used to some different older appliances that are fairly low tech, there can be some difficulties in understanding the installation manual. You know, there could be multiple pages on just programming your thermostat or your remote. And so not a lot of people want to go for that. And then the next slide is for heat pump resources in general, because all of these dependencies mean that your approach is really individualized. So you're going to be the best advocate for yourself, whether you're a builder thinking about your client, you need to be able to speak pretty knowledgeably with your mechanical contractor, or likewise, if you're a homeowner, you want to be able to advocate for yourself. So we can go to the next slide. There we go. And this presentation will be emailed out to everybody, so you don't need to try to hurry and write down all of these websites before we switch slides on you. But I do want to pick out a couple specific ones. So we have the Alaska mini split heat pump calculator. And this is a really useful one because you can put in some general inputs about your home and get a pretty good determination on whether it's going to be a good fit for you. As I've said before, your heat load or your cooling load, it's specific to your house. And so if anybody tells you, oh, you're 1,000 square foot house, you need this. And if they haven't really looked at your house, looked at your orientation, how many windows you have, even where you live, they're making a pretty gross exaggeration of what you need. So you have to drill down a little bit into what your house actually needs. And that goes hand in hand with some of the differing manufacturer numbers that Vanessa mentioned earlier. As you can see, a manufacturer may say this will cool 1,000 square feet. But if you look at the fine print, they said that was in Texas during the winter. So you do want to make sure that you're looking into that sort of detail. And then there's a few lists through some organizations, the Northeast Energy Efficiency Partnership. They actually have a list of heat pumps that have to pass a certain number of parameters to be considered appropriate for cold climates. So it's a good way to get an idea for what manufacturers are making products out there. So when you start to talk to mechanical contractors and you understand what their manufacturer that they typically install is, then you can make sure that it's probably going to be on this list. And then we can go ahead and go to the next one. Oh, we're back. There we go. And so all of that is kind of focused on the design aspect of, is this heat pump appropriate for you? And so consider at this point that the ductless heat pump is a good fit for you, whether you're an existing home or a new home. Now, how do you actually install it in a way that's going to be ideal for the homeowner and ideal for long-term use or maintenance? So a few things that are important, as Vanessa mentioned earlier, in Alaska, how much snowfall you get is really important. You really don't want to put it on the ground where snow is going to reach it, especially during times of operation. So if you get excessive snow in November, while you may still be running the heat pump, you want to make sure it's got plenty of clearance off the ground to get it from there. And people either manufacture their own kits, or you can buy one from a commercially available supplier. And so you can see in this picture, there's a commercially available kit. And so you can actually attach it to the house, which may come with some drawbacks. You're going to have increased noise if there's not like vibration dampers that are installed with that. You want to make sure wherever it's going, that as it defrosts, it doesn't shed water and ice onto anywhere important, like a walkway or a porch or something. You don't want to interfere with that. And make sure that as things defrost in the spring and you have the ability to use it again, that you're not creating a water problem for yourself, depending on where it's attached in your house. As I said, we want to have it be secured, whether it's on its own or to the house. And so this one's got a little bit of an integrated shed roof on it. If you can see on that picture, some people make their own little shed roofs that go over it. The important thing is that you don't block the airflow. Every heat pump is different from every manufacturer on the clearances they allow, but every single one of them needs a certain amount of airflow to operate as intended. So you just want to be aware of that. And then lastly, as you select where this is going to go, ideally it's relatively close to where the indoor head is going to be. There are some manufacturer minimum distances and maximum distances that you have to think about, but you also want to make sure that you're not installing it on the side of the house where the snow tends to fall off in the spring and it's going to crush your heat pump. So there are a few things that you just want to make sure it has to be a site-specific install to pair with your site-specific design. And I think on to the next one. And so we kind of want to round out all of these recommendations on how to actually select your heat pump and where it's going to go and pair all of these things together. So we always talk about energy efficiency in general. It's one of the best things to do first, whether you're thinking about installing a heat pump or adding solar. It pretty much tends to be one of the quickest paying back measures you can do and always increases the comfort in your home. And so pairing the building efficiency of the house along with the design load of the house really lets you hone in on, is this heat pump going to work out for me? And then we want to optimize the airflow throughout the house. And so if you have a house that has lots and lots of rooms, a ductless mini split may not be a good fit for you because you just won't be able to get an even temperature distribution throughout the house. And then as mentioned before, we want to make sure that the install can be as great as possible. And I think that takes us on to the next poll.
Yeah, that's a pretty short poll. And just looking at the time, Lauren, could we do like 10 minutes of questions? And then I think we're going to take a short break before doing the second half of the class.
Sure, sounds good.
Okay. And I can actually start off because I got one question in the chat directly to me that at least that I caught. Connor, it's for you. And because I can't remember what the new one is, but it was what refrigerant are heat pumps switching to now that there's new climate standards for refrigerants. But we were just talking about this, so I know you know the answer.
Yes, that's a good question. So still on the market is R410A. That's been the conventional refrigerant that's used for the past 7-10 years or so. So the market is changing, and there's going to be a few different options available. It's going to depend on your manufacturer, because the way the regulations are playing out is it's a little bit open-ended. So essentially it's going to be the first manufacturer to dominate the market with their product. They will likely become the most common refrigerant in the coming years. And so R410A is a blend refrigerant. So there's a constituent refrigerant in there, R34, and that is one of the low global warming potential refrigerants that is being looked to as things move forward. That probably poses a good transition refrigerant. You can even use CO2 as a refrigerant. It's basically specific to its applications. So the long and short of it is it's not immediately clear what the next main refrigerant is going to be. Maybe a few options. If you look at Europe and Asia, they've already moved on to some other different refrigerants. So it's pretty much cutting edge here. And you'll see over the next year or two that new options are going to be offered.
Lauren, was there any other questions? That was the one I managed to catch, but I haven't.
Yeah. So the first question in the chat was someone saying, I heat with wood and monitor heaters. Would I need a forced air or hot water system to take advantage of a heat pump?
So the short answer to that is it depends. I think that might have been early on in the presentation because we did go over it. It really drives down to what your house is like and where you live, and even down to some of your personal habits on what temperature you like to keep the indoors at. So simply knowing what you currently have doesn't necessarily mean you're a good fit for a heat pump, but it doesn't rule you out either.
Cool. The next question is about the general costs of heat pumps. We had some people in the chat mention about $3,000 to $4,000 for an installation, but do you have any other estimates?
Yeah, I can take that one. So for a ductless heat pump, it is pretty analogous to installing a Toyo stove. And just like Connor was saying, it always depends on the situation. Certainly manufacturers offer different models. You can pay a little bit more and have a drain pan heater. A bigger capacity heat pump will cost more, but yeah, on the low, I would say 3,000 is definitely on the low end. And then, up to 5,000 more average. And then they can certainly go beyond that, especially if you're looking at a multi-head type installation where you have more than one interior head. There are programs starting up to kind of help homeowners with the cost of heat pumps. So if you are in the Juneau area, they do have one program, the Juneau Carbon Offset Fund, that installs heat pumps in low-income housing. So if you're income qualified, you can actually get a ductless heat pump, mini split heat pump for free, which is really nice to offset some of your oil heating or your electric baseboard heating. And then Juneau ran a thermalized campaign that CCHRC was a part of that kind of tried to facilitate a bulk buy to bring that price down a little bit for everyone, not just of the heat pump, but the vast majority of houses that get a ductless heat pump, you end up also needing to pay an electrician, a couple $100 to $1,000 to add that extra circuit that the heat pump is going to use onto your electric panel. So in other areas, it kind of depends on how competitive the market is and your installer.
And someone else asked if you have an estimate for how much a domestic sized ground source heat pump would cost.
A lot more. Okay, so yeah, ground source heat pumps, you know, the appliance itself is not that much more expensive. So you can think of it the same as buying like an oil fired boiler or furnace. So maybe around $10,000 if you're looking for one for like a medium sized house. The issue with ground source heat pump installations that you have to put in the ground loop. And that can definitely run you another $10,000 to $20,000. So, you know, like total of $30,000. I have not followed installations in other areas of the state as much as Fairbanks, but I can speak to Fairbanks. When the price of oil was high, there was a couple things, you know, so this is like back in, you know, 2008, 2010, there was a few things working in favor of ground source heat pumps, especially for homeowners that are looking to have to replace a boiler or furnace anyway. If you're looking to have to replace your boiler because it's old, you're $10,000 in the hole anyway. And so, you know, you could put that toward a heat pump, a ground source heat pump. And at the time, there was a pretty good federal tax credit that could take off another several thousand. And so it kind of got the, you know, your like money out of pocket down to like 15K. And there was an installer here doing quite a few installations. He actually had enough business that he was able to buy a horizontal drill rig, in addition to a vertical drill rig, which was really nice because you didn't have to dig up your whole yard to put in trenches. It just was like a header trench, a footer trench, and then the horizontal drill rig did the rest of the work, and that also brought the cost down. Unfortunately, as the price of oil fell, fewer people in Fairbanks wanted ground source heat pumps, and so that installer does not really do too many installations these days, and as a result, his price has kind of gone back up. Similarly, with ground source heat pumps, there's not these incentive programs typically that you are starting to see with the ductless heat pumps, you know, like the rebates from the utility or anything like that. But that being said, ground source heat pumps are a great option for cold climates because the ground temperature is a lot more stable than the air temperature. So, you know, it may be something that as oil gets, you know, the oil prices rise again, we see a little bit more movement in that area and some less expensive prices in the coming years. But yeah, that's just speculation on my part.
Awesome. And then someone else asked if wind affects the efficiency of heat pumps.
Yeah, it does. And manufacturers sell wind baffle kits similar to mounting it on your wall. There's pre-made ones, or if you're enterprising enough and you want to build your own shed roof, you can provide yourself a wind baffle. The main thing is you want to look at your install manual and make sure that your clearances are being met, because you need to set the wind baffle far enough away to block the wind, but also be far enough away to allow the heat pump to displace air around it to actually get efficient heat exchange.
Awesome. And then it looks like we have a question about the noise with ducted heat pumps. If there has been any improvements in like if newer systems are less loud.
Definitely. So it's for sure a historic complaint that compressors outside, you hear your neighbors when it cuts on. They've got a really inefficient house. It's going to be coming on a lot. So the more efficient your house, the less that's going to run, to get some noise savings right there. But the newer technologies, they are getting extremely quiet with all of these ECM motors and things like that. But essentially, the smaller the unit, which is what tends to be the case for ductless mini splits, you can get large ones, but more often than not, they're smaller than the traditional split systems. So you may see like a 5-ton split system. That's what you're thinking of when you're thinking of a really loud compressor outside. But looking at these smaller 1-ton, 1.5-ton mini split systems are going to be much, much quieter.
Great. And then another person asked, so in Europe, they're using drinking water wells for ground source heat pumps. Has that technology become available in the US?
Yeah, that would be called the open loop system. So it's been around for a while. As with everything, it's site dependent on whether that's going to be effective for you. It looks like somebody mentioned some of the drawbacks is you've got to move a lot of water. So depending on the quality of your water, you might have to have, a filtration system to make sure that your lines don't get clogged up or scaled or things like that. if you're in a water scarce area, it's not ideal to be pumping out your groundwater. So it really depends on what's around you, what's available, but that technology is out there.
Yeah, and I can add a little bit to that. Certainly if you install that, it's probably going to add a little bit of cost because you're going to be working with DEC on getting the proper permits, permits that you wouldn't necessarily have to have for like a ground source heat pump. But there's been some really creative installations of like open water heat pumps. One's in Juneau with the NOAA science facility down there. They have to pump seawater through their building anyway for the tanks. So it gets filtered as it's going through their building. They have to filter it on the way out. So kind of its last stop is actually to run through a heat pump and they pull the heat out of that water before it leaves their building. And so it's one example of, they have the filtered water available already. They've already gone through everything permitting in order to be able to dump it outside. They were able to put a heat pump on that water source and also make it into a heat source. But for residents, that's not always, you're not pumping thousands of gallons of seawater through your house. But there has been some cool installations of open water heat pumps in Alaska.
Awesome. And I think our last question for this section, can someone please explain what exactly a mini split heat pump is and why it's called that?
Sure. So probably been using a lot of similar sounding terms here and using some of them interchangeably. So essentially you've got heat pump systems. You can get an air source heat pump or a ground source heat pump. In the air source heat pump family, we've got split systems. So that's what most people who are already familiar with heat pumps in homes, that's the traditional systems. That would be a split system. And then we have the mini split systems, which the ductless system falls into that category. And essentially, why it's called a split system is if you think of a furnace, there's no outdoor compressor or anything. So everything is in one ducted loop inside of your house. And now when you add in the air conditioning or the heat pump component, we've broken apart that single system. We've got the compressor outside, we've got the evaporator inside. And so we've split it apart. And now that we have these smaller systems, you can get ducted mini splits or ductless mini splits, but there's a few different variations, but more or less, a lot of those words tend to be the same. Ductless heat pump, mini split. People tend to be talking about the same things. One of the reasons why these classes are great is people will be able to use those terms a little bit more effectively. I know sometimes I'll talk to a family member and I'll ask how their house is going. They're like, oh, my boiler's doing great. And they go to visit. Turns out they've got a furnace, but they just call it a boiler. So we do have to be a little careful in how we refer to things.
Thanks, Lauren, for doing questions. We're right at the halfway point. So we do have a short break because our second half on energy efficiency is a little bit shorter. So see everybody back here in 10 minutes, just right at 6:40, we'll get started again. Thanks. Oh, there, recording thing. We did have some poll questions if you didn't catch them at the beginning of the break. It is really nice for us if you answer the polls because we are trying to get back to offering this class series twice a year, fall and spring. During COVID, we kind of cut back to just offering the classes in the spring. So we're trying to get a little bit of an idea of formats that work for people and some topics that work as well. Connor, are you back? I'm going to start talking, but you start talking after me, so I'll make sure you're still here.
Go for it.
Okay. All right, guys, we'll get started on energy efficiency. So we have a saying around here at CCHRC that, if renewable heating appliances are great, solar PV is great, but at the end of the day, the cheapest best form of energy is the one that you're not having to purchase in the beginning of the situation. So, that's energy efficiency, and we certainly always encourage people to do energy efficiency first, or even if you end up using renewables to get some energy savings right off the bat. Energy efficiency has a lot of advantages, even in the long run. So definitely cost is a big one for energy efficiency. When you need less energy, you're not having to pay as much for it. Some advantages of doing efficiency before completely retrofitting your heating system are that it usually allows you to buy that smaller, cheaper, less noisy heating appliance. And I mean, we could be talking about a ductless heat pump, we could be talking about a ground source heat pump, we can be talking about an oil-fired boiler. In any case, just reducing that heating load, it allows you to buy the smaller, less expensive appliance. Some electrical considerations. Certainly with a heat pump, you're using less electricity. If you had an electric resistance heating appliance, you're really using a lot less electricity, but even with like combustion appliances, if they're having to come on less often, you use that less electricity. And there certainly is a lot of housing these days moving toward electrical heating appliances such as heat pumps. And so depending on where you live and what the grid is like, doing those efficient retrofits, it opens the grid up to more electricity being used overall. And, not only just for heating, but, as electric vehicles are coming online and people are purchasing them, having more of that electricity available is really nice. And, it's not true for every utility in the state, but, if you're in a location where there's a limited amount of hydropower and the utility is trying to manage demand, efficiency is a way to bring that demand down to be able to accommodate more things like heat pumps and electric vehicles. I'm sure we all saw pictures of some of the crazy weather that we had this winter. Certainly here in Fairbanks, we had like a week-long rainstorm that brought power outages to a lot of people. That Mat-Su Valley, I know, had a lot of high winds that resulted in power outages. So one advantage to efficiency is just when the power goes out and your heating appliance isn't necessarily working, if you don't have a wood stove or something like that, you can maintain that interior temperature a little bit higher for a little bit longer, and hopefully avoid having your pipes freeze. Just other things that we talk about with efficiency, you get that more durable building that's lasting longer, staying good quality, improving health of your occupants with better indoor air quality, and just reducing those cold drafts so everything's a little bit more comfortable overall. Now, there's certainly lots of efficient retrofits you can do to your house. Everything from replacing the windows to, getting off your siding and increasing your wall insulation, going around weather stripping, etc. Some common ones, if you're just kind of talking about the average house in Alaska that we tend to see having a high payback, are listed here. And we're just going to talk about, Connor's going to talk about some best practices for these. Anytime that you can air seal a house, it's always really nice. If you have a really leaky house, you've got a lot of cold drafts, a lot of outdoor air just coming straight in. So being able to seal those leaks, keep your heat inside your house, that's always helpful. You still want to ensure that you have fresh air coming into your building. So as you air seal, you'll want to add in that ventilation, but controlled mechanical ventilation does have a lot of advantages over air just leaking in through the walls. For one, we can use heat recovery ventilators, energy recovery ventilators. so that as we're exchanging airs, we're exhausting that stale air and bringing in fresh air, we can recover the heat from the outgoing air and put it into the incoming air. So unlike air just leaking through a wall, we're losing a lot less energy there. Controlled ventilation, these days it comes with timers. They're very smart. Some of you can program it to exchange less air when you're out of the house at work, when you're on vacation. Some of them are, they'll even have like a carbon dioxide sensor where they can sense CO2 going up. If you're like having people over, they can increase the fan speed, get you more fresh air. Once it senses that CO2 going back down when people go home, they'll bring that fan speed right back down. And another advantage of this controlled mechanical ventilation is that you can put filters in it. We talked a little bit about this with heat pumps, but anytime you have like a heating recovery ventilator, you can stick a filter box on there. And if you're located in the interior where we can get those wildfires and PM 2.5, being able to put a filter box right there on your ventilation system can just, keep those pollutants right out of your house from the beginning. Attic insulation is another one that tends to be pretty good bang for your buck in Alaska. Heat rises, right? So you do see heat going up and out of the roofs of houses. So putting attic insulation there can just help keep heat in your building for a longer period of time. And then the last one, not every house has a crawl space, but for those that do, it can be a big moisture source for your home. So putting some insulation down there can help with energy, but this one we tend to see some pretty good paybacks with the building durability side, and that we can control that moisture right from the beginning. Those vapor retarders can also help with things like radon, and the same thing with the ventilation there in the crawl space. So that one's kind of a double benefit in that in addition to increasing our efficiency, we can also work on our building durability. I'm going to pass to Connor here to talk about some best practices for each of these retrofits, and then we'll end with questions just like we did with the heat pumps.
Thanks, Ness. So before we dive into a few of the specific energy efficiency measures, I want to cap off what you were talking about with ventilation. So the order of priority on the house generally follows a top-down rule, but it can, again, vary depending on exactly where you're located and the features of your house. But generally across the board is you need good air quality in your house. And how do you go about doing that is you ventilate your building. So you bring in fresh air from the outside, and you can do that in 3 ways. 2 of those 3 ways are acceptable in Alaska. So familiar with the Alaska Housing Finance Corporation's building energy efficiency standards, they lay out some specifics as you want to avoid what's called supply only ventilation. And so the preferred methods in Alaska or any other colder climate is exhaust only ventilation or balanced heat recovery ventilation. And the idea behind that is your interior air is warm and humid compared to the outside or colder temperatures. And so you want to prevent having your warm, moist air exfiltrate through your building envelope and then condense in your walls. And once you get condensation, you got prolonged water exposure, can lead to things like mold and rot. So how do we actually go about ventilating things correctly? So generally the easiest one to implement is exhaust only ventilation. This tends to be because people already have bath fans in their house or they've already got a range hood for their stove. And so you can use those more often than just kind of on demand when you go into that room or when you actually cook. You can, as Ness mentioned, hook them up with a timer or have them on some more other schedule that you've come up with. Moving beyond those into a bit more of a complex situation, as you can see pictured bottom right is a heat recovery ventilator. And so that represents a balanced approach. So you're exchanging air between the inside and the outside at an equal rate. So you're not depressurizing or pressurizing the house. This is especially important as you begin retrofitting your house and air sealing things, because with combustion appliances, you run the risk of making your building so tight that you can starve the combustion system of air that it needs. And when there's only a certain amount of air available, air that you need to breathe and combustion air that appliance needs to use, the appliance is going to beat you out for prioritizing that air. So we want to keep our buildings healthy and safe by not depressurizing them because we want to prevent that backdrafting. And so you can achieve that through a balanced ventilation system. Heat recovery systems tend to be more common in Alaska. Energy recovery systems, or ERBs, are starting to become a little bit more common. They're slightly different, and they have had a little bit more problems in colder weather. So that's why you really don't hear about them that much up here. But we can go to the next slide. All right, so as I said, we're kind of taking a top-down approach through the house. We're air sealing everything first. Ideally, you're air sealing all aspects of the building envelope, but you tend to be able to pair that with an attic insulation retrofit at the same time, especially if you have a vented attic with easy access. It may be poorly insulated in the first place, or hardly any insulation. Maybe there already is insulation for a retrofit, but nobody did any air sealing first, because you've noticed that, oh, I got cellulose blown in a couple of years ago, but I'm still having ice damming problems. That could be related to a couple different things, but probably you've got some air leakage in your house. So your warm, moist interior air is moving through your ceiling plane into your attic. And so it is important to air seal that first. And when we start at the top, we reduce the stack effect, which is the exchange of air vertically through our house. Our house functions as a chimney, essentially, in the winter. So hot air will exit through the top. And so we're starting up there. We're going to air seal everything first, and then move that. There we go. So as we're thinking of this in a retrofit scenario, if you're not going to be doing any air sealing in the first place, you want to try not to mess up the older insulation that's already there. Certain insulations perform worse when they are compressed, and it can be either a little or a lot. So if you have a blown insulation scenario in your attic and you're trying to cap that off with at least R20 more of insulation to make it worth your while, you want to make sure that you're doing a good job of distributing that insulation throughout the attic, and probably like going back behind yourself and making sure that you don't have like massive footsteps through all the insulation. So you essentially compress that down. It's not going to perform as you want it to. And so this is thinking in a vented attic scenario, but one thing you want to consider is the performance of your insulation. So if you're coastal, cellulose may not be the best fit for you, because it tend to be a lot wetter environment. You may want to look into fiberglass. It really depends on what's available in your area, and the costs. If you're in a pretty rural location, cellulose is great, but it can be heavy. So fiberglass may be more beneficial because you're going to fly some bags out or something like that. So you do have to consider, multiple aspects of how you're going about doing your retrofit. Next slide. And so we've taken care of the top. We're kind of looking at the bottom. This focuses on the crawl space. Pretty much applies exactly if you have a basement. And then if you've got a slab, the concept of taking care of air leaks at that level of your house still applies. But essentially here, if we're going to add insulation, we're going to install a airtight and vapor retarder down there. And then you want to make sure that your crawl space, especially if you're in some of the more humid south central, southeast locations, you want to make sure that that crawl space has the ability to get dehumidified. And so whether that's through a mechanical ventilation solution, or you actually have a dehumidifier down there, because you don't want to go through all this effort and cost to go through this retrofit. And then you've got a situation where you're creating condensation in your crawl space, because that's actually leading to deficient air quality in your house. So on to the next one. And so similar to what we had before on the heat pumps, here's a semi-comprehensive list that you can go through on your own outside of this presentation. Those are all hyperlinks that when you have the presentation in hand, you can follow those to the website. And essentially, you want to start just like if you're sizing a heat pump, you've got to think about what does this house need and what's appropriate for it. So we're going to determine the ventilation rate for our house, and it's based off different standards, but there's some free tools online. So I've linked to one here, or you can use conventional standards. They have formulas, which is based on how many bedrooms do you have in the house, how big is your house, and all of that will determine how much outside air do you need to exchange throughout the house to maintain optimal air quality. And so now that you've figured out how much exactly how much air you need in your house, we're going to be moving on to the installation component. So you want to make sure that you're maintaining air inlet distances that are safe. So when you bring in that outside air, you don't want your air inlet to be right next to your fuel tank, or you don't want it to be next to the exhaust fan for your bathroom, because otherwise you're just creating this short circuit loop of unhealthy or stale air. So you want to make sure that your exhausts and your inlets are plenty far away from each other. You're not exhausting right next to a window or a door, or that you're not bringing in air next to your neighbor's combustion outlet or your own combustion outlet, things like that. And we want to think about, when we've established where the ductwork is going to go, that's going to bring in this outside air, or it's going to exhaust it, where are we going to actually put this unit? So obviously you want to minimize the amount of ducting you use in your house. So you want to put it close to the entrances and exits for the air. The shorter we keep those runs, the more efficient the system. And then ideally, we want to make sure it's in a location that is also of good air quality. So putting in a garage, maybe not the best fit, because the system is likely not to be 100% airtight. It's just really difficult to get it that way. Garages, basements tend not to have the best air quality. If you've got a finished basement, it's a different story. But I'm thinking of a semi-conditioned basement or a crawl space. If it's not a great location, you run the risk of basically distributing that air through your house. So you want to make sure that you're putting it in a good spot. And just thinking about with all things, so a power source location. So since this is thinking of this in a retrofit scenario, you're putting this in somewhere. Do you have any space in your panel? Where is there room in a circuit or something like that? If you're pairing this in with a ductless heat pump, now you're really considering, does my house even have the capacity to handle all of this new all-electric components? Because you need a double pole breaker for your ductless heat pump, and you need another breaker for your HRV. So you really have to think about, as I bring all these systems into the house, how will they interact with each other, and where can I put them all? And so just like with heat pumps, we want to consider the floor plan of your house. So the more open your floor plan, the fewer ducting runs you have to do, because the air is essentially already sharing readily with the other locations. So basically, if you have lots of hallways and bedrooms and things like that, you just want to ensure that air can move freely throughout the house. It's generally done with door undercuts and things like that. But say you've got carpet in your bedrooms and that kind of interferes with the undercut of the door, you may look into what's called a return air pathway. And so that's either as a transfer grill or some sort of duct that just allows a bedroom to be connected to the main living space, and it just allows free movement of air throughout the building. When thinking about balanced ventilation, are you going to use this to exhaust air for your bathrooms and eliminate standalone exhaust fans? If you already have them, and this is a retrofit scenario, you may want to keep those, even though it's not the best from an energy efficiency perspective, but the redundancy is good. Appliances do break over time. So if one does go down for maintenance, then you've got another system in place. So there's always good to have some resiliency there. For HRVs, they do produce condensate as the heat exchange occurs inside that core. You can imagine it's kind of like a sponge with those two air streams moving across each other, and the water is kind of wringed out of the sponge. And so you do have to think about, where am I going to put that? And so along the lines of, where's my power going to come from? Where's my condensate going to go? Vanessa mentioned additional filtration. So it's much easier to implement additional filtration in a balanced ventilation system. You can't really coordinate those with a bath fan exhaust strategy. But essentially, if you live in an area with poor outdoor air quality events, then you'll probably want to look into having this filtration installed all at the same time. And then, as with most technologies that we recommend up here, is is it appropriate for Alaska? Is it appropriate for your specific location? What does it do at cold temperatures? Certain units will essentially shut off at colder temperatures. Some units will depressurize your house to defrost itself. So then it's operating just like a bath fan. And so you haven't really done much there. So ideally you want to look for a unit that has a recirculating defrost. So you maintain that neutral pressure in your house and you recycle air for 10, 15 minutes as the unit defrosts itself, and then you're back to getting balanced, fresh outside air. I think that'll take us to the next slide. And so how do you go about figuring out if your house is appropriate for this ventilation retrofit, this heat pump retrofit, all these other retrofits, and then how do we demonstrate the fact that you've done them? So it's done through an energy auditing process. We're basically gathering all the information about your home or your building and plugging it into a computer model, and based on your climate and fuel costs and things like that, we can figure out, okay, how is your house operating? How much does it cost to operate it currently? If we implement, X, Y, and Z changes, how will your house look afterwards? And so essentially you want to get an energy auditor to come out to your house, and they'll take all of the details, and they'll also do an air leakage test or an envelope leakage test, or a blower door test is what it's called. And basically, when we pair the known rate of air exchange that just happens naturally through your building, through leaks and cracks and openings and things like that, we can really dial in what the heating load is for your house. Excuse me. And so then we can figure out what's cost effective to implement, because we've now got your house, lined up to a certain degree. We're like, all right, it's pretty accurate for where we're at, and we can determine that attic insulation retrofit, that looks good, that's going to pay back. That window retrofit, it's kind of expensive, that one might not pay back. You might want that anyways. So you can weigh those options based on payback and the cost effective of the retrofit measures. Locally, many people are familiar with the AK-WARM or ACK-WARM energy modeling software. Excuse me. But there are some other energy modeling options that are out there that tend to follow national programs. So there's ResNet, if you're familiar with that, and the energy modeling softwares that go with that. There is some diagnostic testing, as I mentioned, the envelope leakage testing. If you've already got a forced air system, furnace, then there's going to be some duct leakage testing. If all of your ductwork is inside of your house, it's not necessarily an energy efficiency component, but that will help dial in on the comfort component. If you seal all those leaks, then the air will go to where it's actually intended to go. And then throughout this, they can, your energy auditor can verify fan flows. And so say you want to implement the exhaust fan ventilation strategy or the range hood ventilation strategy. The only way you can do that is if you know exactly how much air those fans are moving in your house. And if you look at the manufacturer's nameplate, it may say, oh, I have 150 CFM range hood, but that's in a lab specific setting with no ductwork attached. So you have to take into account the current scenario at your house. So we can figure out this 150 CFM range hood is actually only delivering 115 CFM of air. So it's cubic feet per minute of air. So we can take that into account and create a schedule based on your known ventilation rate and figure out exactly how it's going to work for you. I did mention it a few times throughout, but combustion safety is important. So we talked about heat pumps at the beginning, which are an all electric heating component, but for the most part, combustion is going to be what you find in Alaska. And so you want to make sure that as you go through all of these retrofits and scenarios that you're maintaining a safe indoor environment for yourself. And so your auditor will go through some combustion safety checks on your house with your appliances, make sure you're not depressurizing excessively for the unit. And then lastly, round out, there are some rebates and financing. So if you go to those few websites, the HFC, Alaska Housing Finance Corporation's website's going to be more geared towards local opportunities. And then if you go to the Desire website, which we also have linked, you can filter by state and you can drill down to Alaska to go there. And I think that takes us into the resource side. Okay, because I did just mention desire, which is the bolded resource here. And so throughout all of these, I'd say with energy efficiency and heat pumps in general, this information is well known, but it's not broadly known, I guess. The people who are familiar with it tend to be very familiar with this type of stuff. So I would say being your own advocate is the best way to ensure that the things that are going to be done to your house, whether you're a builder or a homeowner, are actually going to be effective and efficient. With most things, you want to make sure that you're not getting taken for a ride. Somebody's going to come sell you this magic heat pump that's going to heat your house for free all year long. You want to know exactly how these systems are going to interact with your house. So at the top here, we've got a few different kind of education components, all about buildings, building in Alaska specifically, and then kind of move down to a more national audience. So the Building America Solutions Center, which is more like how-to guides for implementing all sorts of building science and construction techniques. And then, as I mentioned, the national database, which is the Desire database. So there we go. So yeah, that takes us to the next slide. I think we're getting some pen marks here as the presentation's going.
Yes, so for the CEUs, that's back to me. Again, my name is Dana. Here is my email address, dana@cchrc.org. I will be, for those of you who indicated that you want CEU certificates, I will be emailing those to you within the next 2 weeks. Please do check your spam folder, but if you did not receive it, please do not hesitate to email me. And also, if you would like the certificate for the builder CEUs and you did not sign up for it, just email me also.
Thanks, Dana. And yeah, did you want to talk about if anybody has questions or anything? We have some emails there. Have a couple poll questions. Again, just helps us to improve the next classes. And Lauren, I don't know if there was any questions, but if you have them, feel free to put them in the chat or raise your hand and you can ask questions or comments or anything. We have about 20 minutes left.
Yep, it doesn't look like we currently have any in the chat, but feel free to unmute yourselves, raise your hand, throw something in the chat, and we'll get to you.
Lauren, I do see, it's not a question in the chat, but I think it's a comment based on the attic retrofit scenario where somebody said R20 sounds low. It can be low. It really depends on what exactly is there. So that came from some analysis that we've done for, I think it was focusing on the Southeast region, and it was based on a certain amount that was already existing. So in a vacuum, R20 alone is very low. It's not an appropriate amount for Alaska or even other places really. So that's in addition to insulation that's already there. So I wanted to provide that clarity.
I did see a question asking whether there was a before and after thermal image for that slide that had the energy efficiency thermal image of the leaky house with very poorly insulated basement.
Yeah, we do not have an after image of that I'm aware of, unless Connor is. It's an image we use around CCHRC a lot, but I don't know who took it. So
we've had it for a while. If an after exists, we really have to look for it.
Yeah, we should do some good before and after photos of some houses so we could show.
And we did have someone in the chat mention CCHRC's heat pump paper as a good resource, if you wanted to mention more about that.
Good question. We have a couple. They are all in one place and I can't get to it because I'm sharing my screen. So I can't pull it up. let's see. We could drop the link in the chat to, or you know what, I can email it to you, Lauren, and you could email it out with the slides. I'm trying to think which, we have one paper, a couple papers on ground source heat pumps that are a little bit older. Again, just a lot of the research on ground source heat pumps happened when oil prices were higher before they got low. And then of course, in the last couple months, they've really risen again. But those papers are, I think they're still pretty applicable to today. And then in terms of air source heat pumps, we've done a few studies, some monitoring the efficiency of heat pumps, which is pretty logistically and cost, pretty logistically challenging, and also it's really expensive, so it's hard to find funding for that type of work. But then we've done some survey type studies that if you just kind of want to get a picture of where heat pumps are in Alaska, where air source heat pumps are, and a little bit how they're working, how people feel about them, you can definitely go to our air source heat pump website, and we have another one that's a little bit more specific to Juneau with some findings that have come out of the Thermois program. So like I said, I can't copy and paste the link in because I'm sharing my screen, but I can provide the links to Lauren and she can send them out with the slides later.
And I will post the link momentarily, but it is a good point that CCHRC website is a great resource also. So that is cchrc.org. I just put that into the comments. And on there, if you go along the top to the resources and to library, you can put in to the search box heat pump, and then you will see multiple resources that have heat pump in the title. And so the paper is going to be there too. And I will try to, I believe that's the 2017 cold climate heat pump study with Oak Ridge National Lab, perhaps.
Yeah, there's a couple. They're all on one page, Dana. If you go to the project section, and then there's a project, I think in building science, that's just like cold climate air source heat pumps or cold climate heat pumps, and it has all the links there at the bottom. So anyone can search the website too. Oh, thanks, Dana. You got that in the chat. Okay, I'm not doing a great job keeping up with questions. Connor, I think that we have one on, maybe it's a comment. Okay, so it's about R60. That was more of a comment. And Mr. Holland has a question on the more technical install aspect. I don't know, Connor, if any of the resources would be appropriate for that in particular.
I'd say probably the majority of those are geared towards getting your information up. I would say as you move into actually installing these, it's a little bit beyond like typical DIY experience. Definitely a builder with mechanical and electrical experience is going to be able to take it on. The thing about heat pumps, we mentioned it briefly right before the last break, is they involve refrigerants. And so you need an EPA designation to deal with refrigerants. Essentially, it just means if you were to go to a supply house, they likely won't sell you refrigerant unless you have that license. That being said, the internet is a vast place and you can buy a mini split online and nobody's going to ask for your EPA card. But there are a few resources. I would say AC Service Tech is a YouTube channel. And so that's exclusively geared towards the technical aspects. It's focused on the service side, but mini splits are really simple to install. So most of the service side is getting to know the actual components of heat pump. So if you're familiar from that aspect, then certainly you can install it. So I don't think we linked to any of those because it's more kind of geared towards figuring out, is it appropriate for you and where to go from there.
So there was clarification that it is about ground source heat pump and sizing and cost.
Yeah, so for ground source heat pumps and air source heat pumps in general, to be able to know about the sizing and cost to operate, it all comes down to, do you know your building and how that operates? So you're going to build that out either in an energy model, so going through the energy audit process, figuring out what your house is doing. ACWarm or AKWarm, you know, it's not necessarily heat sizing software, but it'll give you a pretty good idea for what you need to install. There are specific softwares out there that are geared towards ground source heat pumps in general, but you need all of that information in hand before you start figuring out, is the 4-ton unit, which would be 48,000 BTUs per hour, is the 4-ton appropriate or is the 5-ton appropriate? Before you even consider those questions, you have to figure out what's going on in your house first.
Okay, there was another question, whether the heat source, ground source heat pump that was installed at Weller School here in Fairbanks, is it still operational? And has there been any cost benefit analysis done since the installation?
I assume it's still operational. Connor, I'm curious if you, the best person to ask this question is not here, so or to answer this. If the person who asked the question wants to shoot me an email, I'm happy to connect you with someone who would know more, but to my knowledge, it's still operational.
As far as I know. And then on that note, for the second part of the question is, have we done anything with that system since? We haven't done any other analysis with it.
All right, another question that appeared is, does a mini split come without a refrigerant?
They come pre-charged with refrigerant, and so it's based on, so you've got what's called a line set. So that's the copper piping that transports the refrigerant between the outdoor unit and the indoor unit. And so you've got some constraints with how far you can go with that. So some manufacturers have minimum distances and there's always a maximum distance. And so they give you a pre-charged amount of refrigerant in there, assuming that you're going to work within the confines of that distances that they're giving you. If you need to go greater than that, you'll need to add refrigerant. If you have a really short install, you may need to take some out. And so anything you do with refrigerant that involves removing it from the system and putting it back in, that's where you cross the line as far as needing like an EPA designation to do it. Essentially, you need a vacuum pump, refrigerant recovery machine, a few other things, but essentially involves pressurizing leak checking systems to make sure that refrigerant doesn't leak back out of it. So the long and short of that is it comes with the refrigerant, it's contained in there, and then you have to be pretty knowledgeable about how to actually interact with it appropriately.
Thank you, Connor. There was a question, where will the recording be available? What location?
Well, our communications director is actually out of the office for a couple of weeks right now. So we are recording the session, and when she gets back to the office, which will be in late April, we're hoping to put it on CCHRC's YouTube channel. So to get there, just if you go to cchrc.org, there's a little YouTube button in the corner, but it won't be available until later in April. So I wouldn't even try checking for a while, because she'll have to basically get it approved to put up and then be the one to put it up.
With that being said, if you saw any links or you're particularly interested in the area, feel free to send an email and I'll pull that information out and get it to you before it gets posted. But it will get posted.
All right, hopefully we have covered most of the questions that were in the chat. If we have not covered them, here's one more chance to put them in so that we can ask our speakers. And in the meantime, we will send out a copy of the slides. And for those people, again, who are interested in the CEUs for builders, I will be sending those out within the next couple of weeks. And if you have any questions, our email addresses are out there, so please get in touch. Well, thank you very much, everyone, and have a wonderful evening.